In this video, I will cover four basic image processing operations. These operations use neighboring pixels to calculate a single pixel's value. And the four operations I will cover are first, mean filtering, second, median filtering, third, spatial filtering, which uses a mask. We'll introduce that topic. And fourth and last, general convolution. General convolution also uses a mask or a kernel, and it has a slightly different algorithm than spatial filtering does, and we'll be covering those four topics today. Okay, so we're going to start by doing an example of mean filtering. And the thing is, with mean filtering, it's very comparable to median filtering. They produce the same result. As you can see down here, this is our original image, this raccoon right here. This is the result of a median blurring, where we apply a 7x7 mask around the edge. We're just going to do a 3x3, and this will make a little bit more sense as we get into it. But this is the operation that we're about to perform is going to be when applied to this original image will result in this blurred image. So let's select a color up here. Let's say the pixel values of an input image are represented like this. So again, we're doing mean filtering. So let's say we want to calculate what the value of this pixel should be. Okay, so the value of this pixel will be composed, the value of this current pixel in the resulting image, you can see it's going to be a 4, but we're going to calculate that by taking the value of all of its neighboring pixels. So we're going to take the value of 11 plus 10 plus 8, and then you see that because we're on the border, we don't know what the values of these edge pixels are, meaning like, what's this, what's this, what's this, what's this. So we're just going to assume a default value of 0. So we're going to make these 0 and pretend like we just extend this image. All right, I'll do a little border here just to make it easier for you to see. But pretend we're going to extend this image, and now we just add zeros to the outside. So let's do some quick math. So we have 1, 2, 3, 4, 5 zeros. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 is 5. Then we're going to add 11, 8, and our 2 10s. All these blue values. When we add them, we see that we come to a 9 plus 1, 2, 3, 39. All right, and then we're going to find the value of this location in our resulting image by dividing 39 by 9. And we're going to round this, and it comes out to be 4. So let's find the next value. Let's find this one. So what we're going to do is we're going to create our fake border to extend the image. Fill these in as zeros, okay? Now we are going to we're going to add all values in every square to create a sum. And then we will divide that sum by 9 because there are 9 squares. So we need to find 0 plus 0 plus 0 plus 9 plus 9 plus 8 plus 10 plus 11. So this is going to be 18. This is going to be 18. So what is 30? And this will be 36. So 36 plus 11 is going to give us 7. 47 divided by 9 is going to give us 6. So hopefully that makes a little bit more sense in terms of how to follow along with this process. If you carry the process out, you will eventually get the same result that I have right here. And so there it is for you. That is mean filtering. So now we're going to discuss median filtering. Again, as you saw in our mean filtering example, we showed the effect of a median blurring on the original raccoon image. So this is the median and the mean. Again, they produce a very comparable effect. we're going to now do the median filtering operation with you. So let's assume that we have an input image with the following values. And again, like we had to do with the mean filtering, when we don't know what these edge values are, we just assume that they're going to be 0. And again, this may be different depending on what algorithm you want to use. But for the sake of this video, we're going to assume that they are zeros. So we're going to have 0 values here. And to calculate the value at this position, we're just going to take the median of all of these values. So we have a 0, a 0, a 0. Let's see, that's 5 zeros. So right there, that's 5. Okay, then we have an 8, 2 10s, and 11. And again, medians, you just take the median value or the middle value. So you cross off the 2 ends, then you cross off the next 2 ends, then you, oh my goodness, sorry, cross off the next 2 ends, then the next 2 ends, which leaves you with the middle value, which is the median. So we know that the median value for this very edge is found in the center, and it is 0. So let's do an example of where it's actually in the middle, okay? So let's say we are right here. We're going to do so we have a 3 by 3 range. That's something that in the previous video, they were using a 7 by 7 range to calculate this image, but we gave the example of a 3 by 3, and that's what we're operating on with this median filtering as well. So let's find the value of this pixel with a 3 by 3 range. So again, that's going to give us the resulting value right here in our output image. So we're going to take an ordered list of all of these values. So we have 2 9s, which appear to be the lowest values. So let's cross those out so we don't repeat them. Then we have a 10 and an 11 and then a 12. Okay. Then we have a 23, 24, 26, and a 99. And again, we cross off the 2 ends once, do it again, do it again, do it again. 12 is now the median value for our output image at that pixel. So there you have it again. That is median filtering. We repeat this process for all pixel values, and when we are on an edge value, we just assume that there are zeros on the edges. That's median filtering. Now we are going to discuss spatial filtering. Spatial filtering is also known as uniform blurring. And again, the input image, once you apply a spatial filter or uniform blurring, it produces an image that looks very much like the mean and the median filtering output. Okay, so again, this was obtained using a 7x7 area. We're going to do only a 3x3 in our example. But first we need to discuss what a mask is. So a mask is a simple, let me draw an image here. Mask is a simple grid. They used a 7x7 grid, we're going to use a 3x3. We can apply whatever mask values we want. So a common blurring mask is all ones. So what this means to say is that we're going to calculate, let's say we have a bunch of pixels, right? That was a pretty poor explanation, but let's take this pixel right here. We're going to make the value of this pixel the sum of all of these values multiplied. So we're going to take this mask value and multiply it by its top left neighbor. This mask value multiplied by its top middle neighbor. Let's do an example. Maybe this will make more sense once we are doing it whiteboarded with a more clear input image. Okay. So we have an input image here. All right, we are going to calculate this pixel's value right here. And again, we're going to assume zeros when we don't know all other values. So let's get a grid right here, because we are doing a 3x3 range. So calculate the value of this center pixel. We're going to apply a mask and divide by 9. So let's take the value of 0 multiplied by 1. 0 times 1 equals 0. Now, what is the value of this 0 multiplied by 2? 0 times 2 is 0. So this is kind of an arbitrary example because you realize these are all zeros right here. So ultimately, the value is going to the sum of all of these. We're going to take all of these values, sum them up. We're going to get 0. Then we're going to divide by 9 because we took 9 pixel values. That's going to give us 0. So we know for this top corner image, in our output image, it's going to be a 0. Let's do an example that will be more meat and potatoes and less fake. So let's take a middle pixel. How about that? That'll be a really good one. So we're going to define our 3x3 grid, and we're just going to apply the mask to this 3x3 area to find the value of this pixel. So let's start by saying, what is 0 times 1? 0 times 1 is 0. What is 1 times 2? 1 times 2 is 2. What is 0 times 1? 0. What is 1 times 2? 2. What is 2 times 4? That's actually 8. What is 1 times 2? 2. 0 times anything is 0. 3 times 2 is 6. 0 times 1 is, oh, tricked you, 1. Okay, so now we're going to take the sum of all of these values. So we have, this is a 4, this is a 10, this 4 and this 6 is a 10. So we have the value of 20 right here. Then we divide by 9 because we took 9 pixel values. And that's going to give us, we're going to round it. And here you can see I have said it was 20, but ultimately when you produce this image, when you print it, you want to divide every cell by 9 in Python. So this would be the output image of just the sum values right here. These are all the sums. But when we divide by 9, when we print it in Python, it's going to give us this correct uniform blurring, but because we applied a 3x3 range of a mask, ours would not be a 7 by 7, it would be a 3x3. So there you have it. That is spatial filtering, aka uniform blurring. Okay, now we're going to cover general convolution. General convolution is my favorite of all these because it's not just a boring blurring filter. You can do a little bit more with that depending on what mask you apply. So let's say that this is our original image, like we've done with all the previous examples. you can change the mask and get a different resulting image. So here, we're saying a pixel, the center pixel will be the average of all of its neighboring pixels. That applies a uniform blurring. Here, we are saying, let's make this center pixel extremely important. Let's not care at all about its corner pixels. And then we're applying a different kind of mask right here to do what's called sharpening. So I like sharpening a lot better than blurring. It looks more pretty to me. I'm sure there's a use case for both, but we're going to cover an example of general convolution applying these masks in a different way than we previously saw with spatial filtering. So let's walk you through an example. And this is a different algorithm than just line it up and calculate it with a mask, where you do the top left with the top left and the top right with the top right. This is going to be a little bit different. So we have an input image, okay? The thing is, with general convolution, these edge pixels are not ever going to be calculated for the sake of this problem. I'm unsure if that applies to most filters in real life, but what this is going to say is, it's going to say on our image, all these border pixels that are along the very edge are going to remain unchanged. They're going to be the exact same that you find in our original image up here. So because they're unchanged, that's okay, because we need them to remain constant, stable for this calculation we're about to do. Okay, let's try to calculate this value in our output image. You can see that it's eventually going to become -2/9, but we'll walk you through what that actually means. So let's draw a 3x3 grid, because that's what we're going to apply. That's the range of our mask that we're deciding. 3x3 grid right here. We want to find the value of this cell in our output image. Again, that's going to be right here. That's where it's going to match up. Here's what we're going to do. We're going to first take the value of the top left item and multiply it by our kernel's bottom right value. So 0 by 0 is 0. Okay. Next, we're going to take our top middle and multiply it by our bottom middle. 0 times -1 is still 0. Our top right will be multiplied by the bottom left. 0 times 0 is 0. Our left middle will be multiplied by our kernel's right middle. 0 times -1, 0. Our middle value will be multiplied by the middle value. So 0 times 6 is 0. Again, we're going to get a lot of zeros for this example, but we'll do one more after this, so you get to see a little bit more than zeros. Our middle right value in our image will be multiplied by the kernel's middle left value. 1 times -1 equals -1. Our bottom left will be multiplied by our top right. Our bottom middle will be multiplied by our top middle. And our bottom right will be multiplied by our top left. Then we sum all of these values that we just pulled. We get the sum of -2. And because we used 9 values right here to calculate the value of this center pixel, we divide our resulting value by 9. So we get -2/9, okay? Now we could have, like we did in the previous version with spatial filtering, we could have just said -2 right here, said 4 right here. And at the very end, in Python, when we're printing the image, we could just divide our entire 2-dimensional array by 9, and it would apply this divide by 9 operation to every cell in our 2x2 dimensional array. But for the sake of convenience, I've just done that for you. But now let's walk through a different example. Let's do a different pixel, and hopefully we'll get more than just zeros. So let's calculate the center pixel. That's a good That's a good easy one. So we're going to draw our 3x3 grid around this. And then one way to help visualize how to apply this kernel to the image is you could just take it, drag it over, and paste it on top. Okay, that's one way I help visualize it, and then I just do the top left with the bottom rights, as if they were on top of each other. Okay, here's the example. If we're finding this middle value, this 2 right here, the value of this cell, actually, not the 2, but let's take our top left multiplied by our bottom right, which is 0. Now our top middle multiplied by our bottom middle is -1. Our top right multiplied by our bottom left, still 0. Our middle left multiplied by our middle right, -1. Our middle by our middle is 12. Now you see that because of this kernel, we really emphasize this middle value. We're trying to magnify it. That's why we get such a large result, which is going to affect the overall value of this center cell much more. Now we multiply our middle right, our middle right by our middle left, gives us a -1. And we're going to multiply our bottom left by our top right, gives us 0. Now we're going to multiply our bottom middle by our top middle, which gives us -3. Now our bottom right by our top left, which gives us 0. So now you see we have 1, 2, 3. So -3, -3 goes right there. So 12. So this is going to be 12 minus 6 equals 6. So then we'll divide by 9 because we have 9 total. But you can see, here we go, we have 6 out of 9. So there you have it. That's that is general convolution. And we just applied a sharpening kernel to our original image using general convolution.